now you made my day. Yeah. Okay. So what we're gonna talk about is just really the aging and its relation to safety and application in second life. And if you go to the next slide, I guess this will trigger our first discussion. Yeah, this is the whole value chain. So what we see here is really, if you look at the far top, is the mining. This is where our value chain physically starts, but practically it starts somewhere else. I will go through it in a minute. So this is where if we go like from mining, we go to having anode and cathode material, and then we start to have cell manufacturing. And in cell manufacturing, the process itself is very comprehensive. This is the green arrows which you see going down, and the cell manufacturing process, because I have seen some questions in the chat as well about why we cannot get some technologies working from the lab into industry. I guess those of you who are familiar with cell manufacturing know the answer, that the cell manufacturing process is really having a lot of sub-processes, and each of these sub-processes has its own know-how, even has its own challenges, and it really takes time and money burning to do a cell. But after overcoming all those challenging and having this in serial production, we end up with what we call here this root file called cell level. And this is where we get from like the upstream to the midstream of the value chain. And afterwards, we try really to make this cell works into a pack. We have different ways to do this, whether we go through modules or we go to cell to chassis or cell to vehicle or whatever, until we reach this right side of the value chain, which is having really a module, or whether it's in the chassis or modules connected together. And then on the right side, we have this BMS integration, battery management system, and we end up with having a battery pack. And having the battery pack, it's engineered for an application. And if you remember, I told you that the value chain starting from the mining, that's correct. But from my perspective, the real value chain of a battery starts from really the application specific engineering. This is what you see on the bottom right of this graph. Because as much as I understand my application, as much as I can influence everything from mining, the purity of the material which I have, the cell manufacturing, to the integration of everything. So I do see the value chain always starting from the application engineering. And then after having my battery working for some time into an application, I can add to it this gold part, which you see on the right down bottom, which is the digital twin. Something which tries to understand how this battery really operates and tries to help the BMS even to have aging and safety perspective of forecasting. Some of them are using physics-based models. Some of them are using equivalent circuit models. Some of them are using machine learning. I have an example of this in my presentation as well. And after the system is operated already, we have three options. We can go to end of life and have a recycling with the challenge of the recycling nowadays, which we have. We can have a disposal of the battery, or we can have second life. So if you can go to the next slide, please. So yeah, those are the three options which we have in hand now. It's really reaching EOL, end of life. We have a huge focus in recycling, but there is as well a discussion about second life. And this discussion about second life, I guess not a lot of people are focusing on it, whether from the EV industry or from the stationary storage industry. It's like not really covered in a mature way. And it has its own challenges, which I tried to list some of them, and really we have to discuss as well how can it be, whether it's a realistic concept or not. This is the first question I have for you, the second life concept, and if it's realistic, what do we need to make it really cost effective and really create a business model out of it? This is the second question which I have. So if we can go to the next slide. Yeah, this is the same part of the value chain, but in a much more detailed way. So if we look from the left side, we have a battery which is really going to different stages to be enabled for having its end of life options. So it have been checked, diagnosis, and there is a basic check which needs, and then there is a second stage of check and diagnosis, and then based on this check, we can try between or select between three main streams. The first mainstream is to repurpose or repair it, and this as well has its own sub stages until it reach a spare part a supplier or an OEM. So for repurposing or a repair, at the end, the people are interested in this are mainly people who are providing spare parts for vehicles, electrical vehicles, for example, or the OEM itself can do this. The second option is having the second life, and by second life, we have to go really into a process of disassembly and check and reassembly of the battery sometimes. And we will see whether we can do this on cell level or module level or pack level. And then it goes into a second life model, which can be a business model, which can be B2B, business to business, or business to customer as well. Or we can have the recycling process into a black mass or recycling facility. Next. Yeah, but to be able really to trigger the discussion, we have to as well to highlight a bit of what is happening in terms of aging. So this is a battery cell. What we see here, I guess it's common for everyone here, but basically it looks basic. And a cathode, which define the battery cell chemistry nowadays, more or less, and an anode, which is basically using graphite, and a separator in between electrolyte and, of course, the SEI layer, which is one of the most important components which discuss about aging. But in reality, if we go to the next slide, I like this picture very much because in reality, what can happen is really a lot. So in reality, the electrochemical reaction which happens inside the battery itself, it doesn't stop even if we don't use the battery. That's why we have what we call calendaric aging, which is the battery ages whether I use it or not, or cycle aging, that the battery can age whether during cycling. And those effects are really a lot. So that's why I like this diagram, because it can show you that there are effects which really take place on the cathode side, on the anode side, in the electrolyte, on the separator, in the SAI layer. But there are two famous effects. If we see here on the anode side, there is this lithium plating effect. This is where lithium accumulates and start to build what we call dendrites. And the second effect, which I need to focus on, is the SEI layer. The SEI layer is the solid electrolyte interface, which is basically for who doesn't know what does it do. It's basically protecting the anode from having a direct contact with the electrolyte. And it's very important, this SEI layer in lithium-ion batteries, because it really can do can consume a lot of my lithium, and as well if it has breaks, it exposes the anode to the electrolyte, which can create some negative effects in the anode side. Next, please. And I personally did try to build a matrix of from different literatures about about aging itself as a matrix. And if we look at the right side, which is not covered at the end, the measurable effect of aging is really having a capacity loss or resistance increase. So this is what I do see in my vehicle, for example. I see a capacity loss that I cannot drive the range which I have, or a resistance increase in the cell or in the battery pack which I have, that I cannot deliver power out of it. So I cannot really do the acceleration needed or power delivery as I do. But to reach this measurable effects, if we look at the far left, there are root causes, and those root causes I do like the categorization that there are use case related root causes, like exposing the battery to high temperature, low temperature, or high SOC or low SOC, or even high currents, or how do you use the energy cycles, or how do I store my battery? And there are production related aspects as well, which can be a root cause into having my cell ages faster or lower. And there are battery design aspects. So it doesn't really end up with the cell design. It's really how do I design my pack as well can really trigger one of the degradation modes or more, which can lead me to, at the end, having fast aging or accelerated aging or not. So the root causes are really the main source of triggering different degradation modes, like the ones which I did explain, like having growth in the SAI layer or decomposition in the SAI layer, or having lithium dendrites or lithium plating, beside many other degradation modes, which can trigger a degradation mechanism or a result to a degradation mechanism, like, for example, loading of lithium inside my cell, which can result at the end into having a measurable effect of capacity loss or resistance increase. And as you see here, the main message here is not to go through each of those blocks, but the message here is that the matrix is really complicated. And that's why understanding aging and what does BMS tries to do to understand this matrix and the root causes of it and to avoid it, and really to see the measurable effects, and even the hard part of forecasting, the measure of forecasting capacity loss and resistance increase, because we have to go down to the root cause understanding. This is very challenging for first life. So you can imagine this as well for second life, which is one of the key challenges as well for second life out of my perspective. So if you can go to the next slide, please. And as I said, I really do want to focus here onto those effects happening in the SAI and lithium plating, because this is one of the key driven for losing lithium, because the SAI growth, if the SAI layer gets bigger and bigger by time, it consumes lithium from my battery at the end, and at the end it's inactive lithium, so I'm losing really capacity. And the lithium plating is really one of the main safety hazards which I have, because the dendrites formatting can really penetrate the electrolyte, the separator, and causing an internal short circuit. And this is one of the main reasons we have thermal runaways for. And talking about thermal runaways, I guess we can go to the next slide, which I do like as well, from the Dyson School of Engineering, summarizing the thermal runaway. As you see this circle on the top right corner saying aging. So aging really participate into causing electrical abuse or thermal abuse of a battery cell. So we have three main sources of causing a thermal runaway: mechanical abuse, electrical abuse, or thermal abuse of a battery cell. And mechanical abuse is mainly having crushing or penetration. Electrical abuse can be triggered through aging, or can be as well forced through overcharging or having internal short circuits, whether it's manufacturing or dendrites growth. And thermal abuse is really having overheating or having my cell not in the right condition of operation. And then this all gets us to thermal runaway, and it's important to understand about thermal runaway that it's not only fire. We have three main components in thermal runaway. We have smoke, we have fire, and explosion. And actually, it could be that people think that fire is the most dangerous thing. From my perspective, it's always the smoke which is the most dangerous thing. I always say if it's black smoke, you have to run. If it's white smoke, you have to run much faster if you have a thermal runaway, because the white smoke from today's chemistry, it really includes hydrogen and sometimes hydrogen fluoride, so toxic and explosive gases, which can really get into explosion and fire very easy. We can go next. The video in the next slide will not work, but this is the initiation of a thermal runaway in electrical buses. It was in China. And as you see here, it starts basically with white smokes, and then if the video is working, but unfortunately it will not work here, it will go into fire, explosion and fire immediately, and even propagate to the next buses. And the bad thing about this is that to control a thermal runaway even is not easy. You need a huge amount of water, and it depends on the chemistry. LFP doesn't produce a lot of oxygen from inside as much as NMC does, so the energy has to go away in terms of to put the battery down. And aging can be one of the main things which can trigger this faster, even in the first lifetimes of the battery. And this is what we're going to see in the next slide. If you go please to the next slide, which shows us this is the Tesla a plant in Australia where it have been, unfortunately, during even pre-operation into thermal runaway. So we do see thermal runaway in electrical vehicles by all types, passenger vehicles, buses, heavy-duty commercial vehicles, or we do see it as well in stationary storage. So the probability is not high. This is what the positive news about this. But once it does happen, it's really uncontrollable in a way that we can really distinguish it easily, especially if we have a EV having this on the mid of the way. That's why we need to control the thermal runaway in the first life, but as well we need to think about it in the second life, because we are talking about batteries going from especially EVs into stationary storage, which is home storage systems, and we don't want to have a lot of uncontrolled thermal runaway events from those batteries in the second life. Can we go next, please? And as you see here, this is basically summing up how degradation happens over what we call cycle aging. So on the y-axis you see capacity, on the x-axis you see this is the time of cycles, and we have three main stages. This is typically, of course, we cannot generalize it, but this is typically what does happen, that in a short period of time, in the first phase, the capacity loss is going rapidly down. And then in the second phase, it goes a bit of linear degradation. And in the third phase, what we call it as a knee point, the capacity really dramatically goes down. And expecting or forecasting what the knee point, when the knee point will happen and how fast the capacity will happen in the third phase is really challenging. And this is the phase which we are as well discussing about operating a second life battery in. So it's a challenge as well to estimate the capacity degradation in a second life battery, beside the safety aspects. Can we go next, please? And I just want to give you a bit of example of a use case. It was interesting tests have been recently announced about exposing some EVs to low temperature as a use case. And if we go to the next slide, I guess you will see exactly what I mean. So this was a test by ADAC, which is a German entity, exposing different vehicles to cold temperatures. There is a full report about this on the website, and they have really just showing the deviation of consumption due to cold temperature. So as you see here, some vehicles were not highly affected, like on the left side of the graph, and some vehicles were highly affected due to cold temperature exposure, like the right side of the graph. And they have done this test as well, exposing the battery, I guess, to the range of operation. Like they have different aspects of testing different vehicles, but the main thing here is that we still have in the market effects on the battery performance due to the use case. And we have to take this into consideration into aging and safety evaluation for the first life and, of course, for the second life. Next, please. Yeah, and as we mentioned, even calendaric aging does count. So if you see here a picture of pouch cells. Those pouch cells, one of my friends did send it to me. He was asking me, okay, I left those cells without using, and I see one of them really getting bigger and bigger in terms of volume. And this is, of course, because of the electrolyte maybe gets into gasification. And the issue here is that he was not storing the cells in the right conditions. And this was not for a long period of time. He was storing the cells in hot condition, and it depends on the cell quality and the SOC level and the number of time which you have not used the cell for without cycling, and the environmental condition of storage you can really trigger some calendaric aging effects, which will prevent you from using the battery in a right way, even if it's brand new. And that's why calendaric aging as well have to be considered even in first and second life applications as well, where we will have some EV batteries stored before it goes to second life applications. Next, please. Yeah, and as we all know, I will not get into the details of the graph here, but different chemistries does have different ways of degradation and as well different ways of reacting to different temperatures of storage. This is what we see here is calendaric aging over period of months and how the capacity loss and the resistance increase does happen in LFP, NMC, and NCA. Yeah, but the main message here is that we have to take care of which chemistry as well I'm using, whether it's in cycle aging or calendaric aging, because there is a difference. Next, please. Yeah, so this brings us to the big picture again. I guess we have now triggered some points related to the value chain and the first life applications from aging and safety. And now, if we go to second life, if we go to the next slide, please, we will see, yeah, we can jump one more, please. We will see in second life, the process itself for enabling second life battery is not easy. And it really has its own, as we have seen, its own sub-stages. And there is a graph which shows these sub-stages in a much better way. If you go to the next slide, please. That we do have in second life many different challenges. We have technical challenges, which are mainly, we have discussed some of them, like the aging of first life or how we qualify the battery to be really make sure that can deliver the capacity needed and the safety conditions needed for its second life. We have economical challenges because nowadays we have the brand new batteries as well in a low cost. And if we do not optimize the process of qualifying second life batteries, this model will never work. We will not create a business model out of it. And it will be always that second life batteries is much expensive than first life batteries. We have battery standard challenges. So there are few standards like I guess the UL 1974, if I'm not wrong, there are very few challenge standards really targeting second life applications, regulation challenges as well, and process challenges and data. And data challenge is huge, but something like the battery passport as well is really solving this issue by forcing OEMs to get the data for us. I don't know how much time do you have for the presentation, or should we stop here and discuss about those challenges in details? I guess, Michelle, you are muted.
Maybe it'd be a good time for a discussion, I would say. Yeah.
Yeah, perfect. Yeah, because the next slides are basically highlighting which solutions we have for those challenges. But I guess it's a good place to have a discussion about those challenges and how do you think about it first of all, and what are the missing challenges as well, which we did not mention here in terms of second life.
Absolutely.
No, I want to jump in here. I just want to thank you for the presentation, Mohammed. And I wanted to ask, like, how good are the data-driven methods when it comes to, predicting the aging of second life batteries? I know the data is on the scarce side when it comes to the second life batteries. Not many people have, done the accelerated life testing on these cells. So what are your thoughts on the data-driven methods?
Yeah, thanks, Ali. I guess I don't want to be the person who answers all the questions. So I would open the question, if you don't mind, for the stage. If someone has a comment on the question before myself, it would be much better because we really want here to trigger a discussion. So I just want to make sure that I understand the question correctly. You are discussing about how good can we do estimation and forecasting for aging in second life. Is that correct?
That's correct. Yeah. Estimating the remaining useful life.
The remaining useful life of second life battery.
Yes.
Yeah. This is a very interesting question. If someone has a comment on this or an idea.
Yeah, I have maybe a comment or so. I was thinking about the same thing too. I think gauging is really going to be the most difficult and challenging part about Second Life. I'm wondering if Second Life packs, if we know what model of cell it is and have manufacturer's data or characterization curves for it, it would be easier to do so. But of course, that also requires the cell manufacturer or OEM to allow to release that sort of data. So that's like from a bottom-up perspective where you're looking at gathering information and data from there. A top-down perspective would be doing diagnostic tests on the current state of the pack, so impedance, capacity, XYZ, and you can triangulate based off of what it is, the state of health of that.
I just wanted to chime in. There are a couple companies developing this technology, but it's in its early phases. So like Rejoule has a tool that does like EIS on battery packs. It's an external tool. And then Smartville also has a tool, but I think it's more based on the battery management system. So there's different approaches to this problem. It's definitely a big one. And yeah, we need more data all around.
Yeah, I was going to jump into predictive analytics is what my company does. So we focus on taking pack level data and making forward-looking predictions on degradation and state of health. And from our experience, yeah, you needed to have some some previous data to work with. A good 6 months or so where you can kind of see how the battery's performed, see what kind of conditions it's been in. And then it comes down to your algorithms and how how they take that data and predict forward. But that's it's an ongoing problem. And for Second Life, kind of like what you said, Mohamed, this is a new field. It's a new area that's developing now, and the demand that's going to be taking off over the next 5-10 years for battery and stored energy solutions. Just making more batteries isn't going to necessarily solve that demand, right? So there's a Second Life conversation that we should all be having for sure.
Mm-hmm.
I think what we're doing here is second. Okay. Just
Well,
to...
your microphone's on, so if you want to.
Yeah, I was going to say. So what we're doing here is we're looking at Second Life and use case. So we're trying to tie use case to Second Life and reduce depending on what it is for. So there's a significant reduction in use capacity as well. So if for example, if we have a capacity of 100 kilowatt hour, a Second Life use case will probably be looking at about 20% capacity of that battery. And that's what we're doing here with that.
I have a follow-up question for you. Where do you look at this, or which country or which application do you look at this?
Right. So I'm sorry, I'm in Lagos, Nigeria. So we don't necessarily have access to data like you do. I definitely not on battery history. So what we tend to do is there's a use case for Second Life, about Second Life relation to reduce capacity.
Okay. Yeah, from my side, I agree to that. I guess even if we solve, this is my own perspective, even if we solve that challenge of having the first life data, I had in my presentation a slide about the battery management system challenges related to aging prediction. We have a problem, or I guess it was mentioned from smart analysis. The people working on this field, they know that to make a model for a battery on the battery management system, whether it's cloud or integrated, embedded on the BMS itself, to make a proper model which can really estimate the state of health during operation, it's very challenging. And having a cloud-based solution can solve this, But if I don't have a benchmark of the state of health of this battery, which comes to me, which I can trust, and train my next model with the data, which can really make an estimation of a state of health, because second life battery estimation of a state of health is, I guess it's a nightmare. I guess it's very challenging. It's not easy. So that's why the battery passport nowadays, I don't know how many of you did hear about the battery passport, but it's really forcing the OEMs of giving the data of the battery pack, at least the basic data over its lifetime, starting even sometimes from manufacturing to the second life applications. But it's not the key thing. It's main challenge to solve to have the data, but I always ask myself, okay, even if I have the data right away from the battery passport, how challenging it will be to create a battery management system which can really operate this battery of a second life under its operation conditions to make it safe and reliable for the user. I don't know if anybody of you works on BMS has a comment on this or not.
I'm hoping that
Because I do see
he's available. Yeah. Fabrizio is CEO of electric vehicles. He focuses on the AI brain for vehicles. Hoping that he's available for some input here.
Hi, Mike. Hello. Yeah, happy to intervene. And if you don't mind to repeat the question, I'll be happy to share my point.
The question was, what do you think about the challenges of estimating a second life battery state of health using nowadays technology for BMS state of the art, more or less?
Yeah, I think it's very important to do so, and there are solutions that are showcasing a very extremely high accurately state of charge and state of health and state of power. But in particular on state of health, we can leverage the cloud to compute a very accurate state of health, in particular if we are leveraging neural network. And this is possible even with a couple of months of history of data points, or even from no history, start picking up some data points along the way. There are also some ways to do a quick assessment when the battery needs to be refurbished. But again, with the advanced battery model and a trained neural network, you can estimate the state of health at any instances, including right before the second life usage. So technologies are there. We use a very deep learning neural network to make it happen, but there are other techniques as well. So I think that's doable and that's coming to market. Yeah.
But how much of data do you need to train your model, and where do you get it from? This is I guess the key aspect here, right?
Yeah, there are companies like Electra that in our case, we build up a database of 1.5 billion data points. We are getting closer to the 2 billion data points that we collected over the last 8 years from 65 battery manufacturers around the world, about 35 OEMs, and about 15, 20 tier 1 suppliers. So if you're talking about a brand new battery that nobody has seen before, that the labs are developing, you need a couple of months to train the model. If you talk about any existing LFP, NMC, cobalt light, enriched, whatever, most of the time you already have a model that can be trained in a couple of charge discharge. So we have already trained the model for most of the available batteries. So you need little time. You need probably a couple of days or a couple of discharges.
Perfect. Yeah, that's very, very nice to hear, at least that you have a benchmark of models already on the shelf, which can be used for existing technologies.
Correct. The industry is calling it AI BMS. We call it EVI, but the industry started to call AI BMS, and we are going to see some commercial players launching that in a year or two from now. So stay tuned.
Okay. Maybe I have a last question related to this. Do you mix between machine learning and physics-based models or equivalent circuit models in this case in the BMS, or do you use pure machine learning models for this?
No, Electra is a pioneer of hybrid. So I've been pitching that in conference for 5-6 years. So our solution is physics-based model plus data-driven. So it's a hybrid mix that nowadays.
It's a hybrid mix.
Yes, has to be hybrid.
Yeah. I always believe that hybrid approach as well, especially what you mentioned, physics-based plus machine learning is the right way to go. Yeah, but I will leave the floor for others if someone has a comment on this point as well.
I have a different topic question. If there are no other comments on this topic, I'm super curious to get people's perspective. Are packs that are ready for second life safer, or are fresh packs safer from a safety perspective?
Tricky question.
Yeah, exactly.
I mean, you have to define what you mean with being safe, and if many define it as thermal stability. But if you actually look into the research, there are studies that show that if we define safety as thermal stability, it actually improves during aging, while other studies suggest the opposite. So it's mixed data in the publications.
That's my general understanding too. So what I've heard overall, at the beginning of life of a pack, you have the most energy, and so you have the highest risk of an energetic failure, an event. But at the end of life, yeah, you have more potential defects, failure modes, such that show themselves due to degradation. Oh man, we have Tristan here. I'm really hoping Tristan can give some insight. He's from Exponent, so that's his expertise.
So we do a lot of modeling of failures and of thermal failures, and the Weibull modulus of thermal failures is typically greater than 1, and so that suggests that your hazard of failure is increasing over time. So I would say that older packs are more dangerous, just based on what I've seen.
Mm-hmm. But Tristan, do you see you say it's more dangerous because of a lot of aging mechanisms have been triggered, although the energy density or the capacity is less, correct? Or what is the point to make them more dangerous?
Yeah, just because there's more, these aging mechanisms are just increasing your chance of failure, of thermal failure specifically. I mean, you bring up a point that maybe there is less capacity there, and so in theory you have less energy there to cause damage, but kind of the way I look at it is if you have a thermal event, like it's a thermal event and it's bad, and it's hard to look at it and be like, oh, well, this thermal event was smaller than this thermal event. So I tend to take the simple look and just say, look at the thermal failure rate of the batteries, which increases over time typically.
I have seen in the chat people asking about safety, and I guess, Michelle, you mean by safety thermal runaway. Especially, this is what you mean by safety, not other metrics like financial, because someone listed financial safety or something. I don't know what did he mean by this, but we're discussing in terms of safety, we're discussing about thermal runaway event, correct?
Yeah. It's a cheeky comment from Albert. If your pack goes into thermal runaway earlier in this life, you can get it replaced because it's under warranty.
Okay, yeah, but hopefully this doesn't happen in a household where someone can really get killed, because we did see incident where batteries did really harm, cause fatal or loss of people. So of course it doesn't happen often, but I mean by safety here we discuss about thermal runaway, correct?
Yeah, absolutely. Mohammed, can you? Oh, go ahead, Ali. Go ahead.
Yeah, I just wanted to say, when it comes to aging, my understanding is that even within the pack there are modules, and within modules there are cells. Each cell also ages differently from the other cells, and when you have a worse cell in series, that will limit the performance of the whole module, and in the end also the pack. So how to address this without opening the pack, because opening the pack and sorting out all the worst cells will increase up the cost, and that will make no economical sense to use second life batteries. Any ideas on this?
Yeah, I guess this is one of the core questions which I did ask as well about. Let me formulate the question a different way. Do we think that second life is realistic on cell level, or if we have a battery consists of different modules on module level or on pack level? So can we mix? Do we think? Let's start with cell level. Does anybody think that really we can open a battery pack with today's design and really get to the cell level and try to mix different cells together to create a second life battery?
No.
That's terrifying. Honestly, that's really terrifying.
I agree with
Yeah,
Tristan.
so-
Absolutely no.
Okay. I'm happy to hear this because
But
this is my opinion.
there's a
always.
distinction between taking apart a pack and using it module by module versus cell by cell, right? There's many different levels that we can look at this by, which I think is what you're getting at.
Cell by cell. Yeah, cell by cell, because really there are people trying the approach of getting cell by cell.
Wow.
I wish them the best of luck.
I do as well. I do as well, because you can imagine that we are welding. I don't know if, but maybe we have a different. If someone really tries here in the room to do build second life batteries from cells, maybe he can explain to us the approach. Maybe we are wrong.
Well, they are doing it, and the consideration is not necessarily safety. Consideration is cost, and it's more disguised as repairing than repurposing. So, and that's what you get. Of course, it's got serious, very significant safety implication. But the consideration here, like, I'd rather do it than get a new battery or do it properly.
From different,
It's not.
yeah, from different cells, you mean on cell level. So they are mixing different cells, used cells into a new battery pack. Yeah. I will tell you an extreme case which I did face, and I couldn't answer this question. So I will not mention the country, but some people did approach me and tell me that we are using really second life approach from different cells. And my main question was that, okay, where do you get your cells from? They say from this and that and those applications. And they were mixing cells that they didn't know even their cell chemistry. So it could be that they are mixing even LFP with NMC with whatever. And they are depending on the cell format size. So as long as it's 18650, we can put them together. And the question for me was that, is it feasible to do this or not? Even from the capacity perspective or the safety, I couldn't answer this. I really couldn't answer this. But I imagine that this does happen in the market.
And there's a very big consideration for the battery industry in general, and that is the image that is projected of the lithium polymer batteries that is not safe. And it really doesn't matter whether it's first life or second life. So if second life is not managed properly, the image gets dented. It gets dented.
Yeah.
I'm maybe just thinking about performance. If you drive all of the cells the same way, if they're in a module together in different chemistries and different ages and state of health, it's a disaster waiting to happen, right? Like, you need to know what load profiles you're applying to your cell, and what the state of health is in order to have a safe operation.
I mean, how would the BMS handle cutoff voltages if you have LFP and NMC together in a module? I don't think this is even a feasible question to ask.
Yeah, exactly.
But I just wanted to make one comment. I don't do it by myself, but I know about a business who actually make packs. I think they do 18650. Not sure, maybe even 21700, and they build out of batteries that have been used, or sometimes they get a module and the module doesn't work, and they just disassemble the module and they see, hey, this is just actually a problem here and there, and the cells are actually fine, and then they're building but it's not different, so it's all the same cells they put together. And the key question they already asked themselves is, so to say, how can we justify costs for testing when new batteries are just not that expensive compared to getting a used one and testing it? And the key is like really automating the testing. So they have a way, I cannot go into details, but they have a way that they can really automate the testing in a smart way. And I don't know the number that they can do, but they can build a few packs. And I mean, I have not seen any safety relevant issues they had so far.
Okay. So one of the key things is to drive the qualification process for batteries, or the testing process, to drive the cost of it down by automating it and make
I
it
mean,
more
this
simple
is
as well.
one part of it, I would say, to have at least an economically feasible thing.
Mhm.
My gut's feeling is still. I mean, we need to say that if you want to have an economically feasible business, if you want a business case, the testing and the used battery should not be more expensive than the new battery. But even
Cool.
if you solve this, that doesn't mean that we have now a safe system. Whatever we mean by safe, that we need to define. But my guts tell me it's workable somehow, but it's not quite easy.
Mhm. Yeah, but let's get to Ali's question that, okay, we kind of like 90% agreed that on working on cell level second life integration, is the answer is no, but there are cases in the market which we have as well cell level integration for second life. But what do you think about module level? If a battery consists of different modules, can we then mix and match modules from different battery packs? Let's assume we are using the same chemistry for sure, and we know, okay, the module are homogeneous together. But on module level, do you think it's more realistic to realize second life application and on back level?
Well, Mohammed, I had a thought on this. You were talking about cell level second life integration, right? So I think I'm not a technical expert, but what I feel is that I think it's not impossible uh, practically to go for second life integration cell level, because if we think about it at the manufacturing stage itself or at the designing stage itself, if you can go for a battery pack where a grid-based structure is made and the location of every cell is mapped earlier. So towards end of life, you can use AI, you can use an advanced VMS system where you can run a diagnostics check and identify based on certain prefed parameters the particular cell, the position of a particular cell, which is giving you a response according to the inputs that you feed. So you can identify the state, the health of each particular cell in a pack, and pick the right ones rather than going one by one, identifying each cell and understanding the second life application of that. I don't know if I've made myself clear.
I love that idea and innovation. The question I have for you, and I want us to consider, so we have, if we're suppose that we have the technology to actually map every single cell in a pack and know where they are sitting in each pack. We have tracing of each of the cell serial numbers, the pack serial numbers, the electrochemical data, that's like the first, like beginning of life data, and we want to sell this to a second life provider. Who bears the cost of storing that data, especially for millions and millions of cells, like thousands of packs? Who bears that cost, and how is that going to be factored into this sale and use of second life?
Mm.
Yeah, that's
It's
actually a
interesting
question.
question.
Yeah, there's a lot of cost associated with it, but I don't know, maybe we have to go for a cost benefit analysis. Especially, the importance of second life applications, the importance of recycling. We have geopolitical issues causing availability of materials. It's a big challenge. So we need to weigh between what is more important, whether it is availability of materials or whether it is the cost involved in going for the right diagnostics. It's tricky. I don't know. I can't answer it properly, but yeah.
Michael, the way I see it is the OEM owns that data, and maybe the cell manufacturer through a data sharing agreement, but the OEM owns that data and they're probably not going to be willing to share it, and they have no reason to share it.
Absolutely.
So I think that's kind of one big challenge of this whole industry.
Yeah, sure. We did highlight this, but that's why the regulations, like for example, the battery passport is really forcing sharing, not all the data, but I would say basic data needed. But people underestimate, but as mentioned, even transferring this data, if the Second Life facilities, the people working in Second Life nowadays, they are all more or less in the startup range or small, medium enterprises. To my knowledge, I didn't see huge entity which really works in Second Life, and they have to store this. And there is a second aspect beside Michael's question is the logistics. People do underestimate logistics costs a lot. To transfer a battery from X to Y places, there is a huge amount of costs which needed. Battery is a hazard good. And at the end, it is treated as a hazard. It's not easy to get it from X to Y, even in first life. And logistics costs plus processing costs plus data costs plus qualification costs as well. I don't know if really this will make this Second Life approach happening as a business, or it will only happen because that, as mentioned before, I guess from Ted, that there is a geopolitical reasons for it to happen.
Yeah, I think long story short, there's probably a reason why companies like Redwood Energy have very clear partnerships with OEMs for very specific models of vehicles. Because a lot of these things are uncertainties are less apparent and more figured out.
Mm-hmm. But still, it's a potential because it could be something that can prolong the use of the battery itself, even in lower C rates. If we can really solve the issues related to, I guess, mainly qualification and testing, but we don't have to underestimate as well the other aspects, mainly logistics and data handling. I guess those are two key challenges people does not look at in a proper way.
I'll ask it here then, is this an opportunity for PROs and extended producer responsibilities that we're starting to see some states in the United States extend outside of just packaging and paper goods and now into batteries as well? Can this extend into what could be a Second Life application of now your producers are responsible for the life management, the whole life cycle management that can go into a Second Life application?
Okay. But I didn't get the point that the producer will be responsible for first and second life, both of them?
For the transportation, data management side of things.
Okay, so he will handle part of the cost of enabling the second life to happen, you mean, correct?
Yeah, as an opportunity.
Okay, yeah, this could be if it's integrated within the cost of the whole battery. Yeah.
Yeah, we're seeing some legislation pop up for EPR for recycling already. Not quite so much for Second Life just yet, but it is pretty clear that there needs to be some sort of policy support for circular economies and the 4 R's in recycling, repurposing, reuse, in order to make it economic viable for the bottom half.
Yeah. And does anybody else works on the approach of the battery management system for Second Life as well, or first and second life? I have seen only one example, but anybody else in the audience have been working on this? Because I think this is a huge potential for a market opportunity. So there is a lot of work needed into BMS, and if Second Life will be enabled, really the need of or the ones will master this process. I guess they will master the whole business, because this is the key thing which we need to make a reliable capacity degradation and as well as safe operation without a thermal runaway or any hazards in terms of second life applications. But the last question I have from my side is that, do you think second life will work more in B2B, like business to business aspects, or business to customer? Or did you see any examples of nowadays working in business to business or business to customer models?
So one thought that I have is whenever you start talking about tearing apart a battery pack, the whole problem looks very, very challenging. And I'm wondering if maybe there's other models of, so to speak, battery reuse that don't actually require taking apart the product. And one thing that I just have in mind, I'm curious what other people think of this, is imagine somebody has a car where the battery capacity has degraded a lot, and they basically take the car off the road, they no longer pay registration fees on it, put it in their backyard, and if vehicle to grid was a thing, use it as basically like a small stationary storage product. Does the audience think that is feasible at all, or other than the fact that like vehicle to grid isn't really a thing yet? If it was, do you think that would be practical?
Is it using the whole vehicle or just the battery of the vehicle in a way that, like, you mean that I really park my car in the backyard or something somewhere and connect to the grid?
Yeah.
As a vehicle to grid application?
I mean, if you think about it, a lot of people have, maybe not in densely populated areas, but in less densely populated areas, a lot of people just keep old cars in their backyard before they scrap it, thinking maybe someday I'll fix it up, or someday I'll let my kid drive it once they have a driver's license. So in terms of space, I think it seems feasible. But
okay. Yeah, I do think that this will happen in some countries, but not all countries, especially in developing economies. No vehicle will stand without being used. People will think about some way to happen, but I guess in developed economies, this could be feasible because you have the luxury of having this vehicle and still buying a new one and so on, and using it as a set itself. It will be even much better and much easier, because at the end if you can profit from the money that you are supporting the grid with this battery, like a running cost, it could be something which can be feasible. So this is my idea. I don't know for someone else thinking in a different way. And I still see people listing in the chat, but I guess it's much better if you just unmute yourself and just join the discussion itself. Because I have a question in mind. I don't know how much time do we have still, because the event itself, I guess, is ending in few minutes, but we can take like few last comments on this point. But back to you, Tristan. I don't know what people think about your concept of using the vehicle itself in vehicle to grid application. If someone have any thoughts, please jump in.
I guess the issue is why are, and maybe this is too early to answer this question, why are most EVs taken off the market? Is it through some graceful failure where the capacity just decreases to some level, or is it some failure like a soft short where the battery pack basically shuts itself down due to safety concerns?
Yeah, but it could be something. But the main message here is that for Second Life, we have not only one challenge, but really multi-dimensional challenges gridding together, and that's why it's not easy to see this concept really being realized in a commercial way. But I believe it will happen in some countries, in some areas as well, where batteries is not easily accessible, especially first life batteries, or there is no recycling facilities, or there is a need really for using it in second life applications. But as I mentioned, a lot of people avoid discussing this point or overlooking it because of its complexity and challenging. So I'm very happy that we had some discussion about it and opening the just spotting the light on it in terms of the challenge of relating it to aging and safety. And I would propose, if no one has any other comments or remarks, that we can end up the session here. And I was very, very happy to have this discussion with you. And thanks for everyone.
Yeah, thanks, Mohamed.
Thank you for a great session.
Thanks a lot.
Thanks a lot. Thanks very much. And I hope to see you in the next events as well. Bye-bye.